everyone, welcome to my channel, The Big Boolean Theory. This video is part of a lecture series on operating systems, and currently we are on the second module of this course, that is process management. Within this module, we're trying to understand that how does the operating system manage the hardware resource, that is the CPU, by providing this abstraction of a process, right? So within the second module, we are currently on the fourth topic, that is process system call API. So, as you know, within this topic, we are trying to understand the set of system calls that the Unix operating system offers, which help us to manage processes, right? All of the system calls, which are the crucial ones, the important ones, not all, the important system calls which are related to the management of processes within the Unix operating system. We are looking at those system calls, right? And till now, we have talked about process creation, and there we talked about the fork and exec system call, right? We saw how the combination of fork and exec allows us to create new processes in Unix. And after process creation, when we looked at the other important operation that is there, that is process termination, right? If you are creating processes, then obviously you would be terminating them. So in the previous video we talked about the exit system call that allows process termination, right? Now in this and the next video we are going to look at another major operations that we want to do in context of processes, is that one process should have the ability to wait on another process, right? So we are going to look at the waiting operation, and as you can see, the system call that we have in Unix for that is wait. So in this video, I am going to introduce you to the concept of wait system calls, and we'll understand how they work with examples, right? So without further ado, let's get started. So let us start the discussion again from this slide. This slide contains a description of all of the operations that are important related to processes and the system calls that allows us to perform these processes in the Unix operating system, right? I discussed in the intro also. We have discussed about process creation and seen fork and exec system call, and then we looked at process termination via the exit. Now in this video, we'll understand how one process can wait on another process, right, via the wait system call. So first of all, before we look at the wait system call at the API, right, first of all let us understand that why would one process need to wait on another process. That understanding is very crucial. So first of all, let's understand why one process would want to wait on another process, right? So now let us understand with some examples of why one process would like to wait for another process, right? And the most important and basic example that I have for you is the Unix shell, right? So as you can see, I have the Unix shell open in front of you. And if you look carefully at how the shell works, is that it takes in a command. It first of all, there is a command prompt, right? This is the command prompt. This is basically waiting for the user to give in some input command, and once you give in a command, it will execute that command, right? And then it will become ready to accept the next command. But the thing is that once you give in a command, it will execute that command, and only when that command is executed, it will go on to the next command. So the thing is, here the shell waits for the current command to execute before going on to the next command. So let's see some example commands to understand this. So let me first of all print out the current working directory, right? Let me list out the files that are there in this directory, right? So let me say hello. So as you can see, these are commands that get executed quickly, right? And so you do not kind of see the waiting thing. But the thing is that in each of these commands, that when the shell is executing that command, it is waiting for that command to end. Let me take a command that will really take some time to execute, right? So let me use the sleep command and make it wait for 15 seconds. So as you can see, currently the shell is waiting for the sleep command to finish, and it will take 15 seconds for that. And until that, let me try to do something else. I'm trying to print the contents of the directory, but it did not happen until the sleep command got over. Only when the sleep command got over, this ls command was accepted by the shell, and it displayed the contents of the directory. Let me do this again for you, right? Here I'm waiting for 15 seconds, and currently the shell is waiting. It will not accept another other commands. Even if I try to give it some commands, it will not accept those. So I have tried to print the current directory. I tried to do a hello, and only so when the sleep command was being executed, the shell did not accept those commands. Only when the sleep got over, it executed the pwd command, and you can see the current working directory. And after that, it accepted the hello command. Right. So this is how the shell works. Right. The interface that the shell exposes to the user is that there is a command prompt. You enter the command that you want to execute, and once you enter a command, it will wait. It will basically execute that command, and while that command is executing, it will wait for that command to finish before proceeding with the next command. Right. This is the interface that the shell exposes, and this is a easy to use interface, quite intuitive, right? So first of all, you would want to do one task and then only go on to the other. So we have seen a concrete example where one process would want to wait for another. We have a very basic use case. As you saw in this case, the shell is waiting for the command that it currently executing. Right, the shell will fork a new process, and that new process will be executing the command that you give as input. So the shell here, the use case is that the shell would want to wait for the current command to execute and then only proceed with the next command. So we have seen with an example where one process would like to wait for another. In this case, it was the shell which would like to wait for the current command to finish. Let's take one more example and also see what are the challenges if we do not have an interface that allows us to wait. Right, let's take a piece of code and see another example where uh, one process would like to wait on another. So let's take another example to see where one process would like to wait for another, right? So here I have a very simple piece of code written in the C language. Let's understand this. So we'll go through the commented code also later, but let's focus on this part for now. So here we have a fork system call, and there is an if else statement. If the fork value returns 0, we want to do something. Otherwise, we want to do something else, right? So we have seen this kind of code. So when the fork returns 0, which means we are currently in the child process, when fork will be executed, a new process, a child process will be created. And in the child process, it will return the value 0. And within the child process, what we are doing, we are printing the dot 1000 times, right? This is a simple for loop iterating for 1000 times, and we are printing dot. In the else case, we will be returning into the parent, and in the parent, we want to print the character 0 1000 times, right? So basically what this piece of code is doing, it will create a child process. In the child process, it will be printing the dot 1000 times, and in the parent process, it will be printing the character 0 1000 times. So what should be the output of this piece of code, right? Think about it. What should be the output? So basically I want basically let's make this assumption or this requirement. Let's make this requirement that we want to write a piece of code where all the dots should be printed before all the zeros, right? 1000 dots printed by 1000 zeros. This is our requirement. Do you think this piece of code will fulfill this requirement? Let's see. Let's run this code. Even I don't know what will be the output, and I'll explain you why. Right. So here I'm executing this command. Let me explain to you this. I'm clearing the screen, and I am compiling this piece of code, this wait.c file, giving it the name wait1, and I am executing the generated executable. So let me execute this piece of code. And as you can see, the output is that the 1000 zeros are printed first, followed by the 1000 dots. What did we want? We wanted the 1000 dots to be followed by the 1000 zeros. Here we have a reverse situation, right? The parent is going first, which is not what we wanted. We wanted the child to go first. Instead, as you can see, the parent is going first. And if I execute this piece of code multiple times, again, every time the parent is going first, but it is not necessary that the parent will go first, right? Let me do one more thing. Let me increase this number of iterations. Let me make it 10,000. We have the same piece of code, but now we have 10,000 dots and 10,000 zeros. Again, I want the 10,000 dots to be followed by 10,000 zeros. All dots should precede all zeros. Can this new piece of code do that? Let's see. Now we have replaced 1000 with 10,000. Let's see what is the output. So if you see, what is the output here? There is no particular order in which the zeros and ones are there. Zeros and ones are alternating. So basically what is happening here, the parent starts, it prints some zeros, then the control goes to the child, it prints some dots, then parent child parent child, and so on, right? Finally the child finishes, and if you execute it, you will see the output is changing every time, right? So the point that I want to the conclusion that we can make here from this example is that when a process creates a child process, both the parent and the child execute concurrently, right? As you can see here, the parent and the child are alternating on the CPU. So when a child process when a process creates a new process, right? So we have two processes in the system, the parent and the child, and there is no particular order in which they will execute. So the decision of which process would be assigned the CPU is taken by a piece of software known as the CPU scheduler, right? It is a component inside the operating system that decides which process will go next, and we cannot make assumptions about what decision the uh, scheduler will make, right? The scheduler is a complex piece of algorithm which decides which process will go next based on multiple factors, right? uh, like what is the type of operating system, what is it aiming for, what is the goal of the operating system, right? What is the user experience that it wants to offer, how many processes are there, several things, and each operating system will have its own scheduler, so we cannot make predictions about how the scheduler will behave. We can only conclude this thing that when we have the parent and the child process in the system, they will be executing concurrently. The exact order we do not know. We also do not know when we how much time will each process get, right? So you can see the amount of time the parent and the child gets is varying, right? And every time I execute this piece of code, the output is kind of different. So there is a non-determinism that exists in the way the parent and the child execute. The only thing we are sure is that they are executing concurrently, but the order, which one will go first, the parent or the child, anyone can go first. How long will each of them execute, anyone, that is also random, right? And the order in which they will switch. So that all of this depends on the scheduler. The only thing that we can guarantee is that the parent and the child are executing concurrently. Apart from that, we have nothing else to guarantee. So there is a kind of non-determinism that exists in the order in which parent and child will execute. So the requirement that we had, let's come back to that requirement, right? We wanted that we wanted to have such a piece of code that will print all the dots and then only it will print all the zeros. Clearly you can see with this code that is not working. That is not the output that we are getting, that is not what we desired. Here all the zeros and dots are jumbled, right? We wanted all the dots to be at first and then only all the zeros, but that is surely not the case. So what do we want here? We want the child process to go first. First of all, that is clear, right? In this case, the parent is going first. And if I basically execute it multiple times, sometimes the child also can go first. Here, the parent is going first, but the child can also go first. It all depends on the scheduler. So in order for this piece of code to work properly, what do we need? We want the child to go first, print all the dots, and only when the child has finished, we want the parent to start like printing the zeros, and the parent can print all the zeros. That way we will have the desired output, that is all dots followed by all zeros. So currently we do not have the answer to this. Currently the code that we have written is kind of insufficient, so we need a mechanism via which the parent process can wait, right? So that is how let's now discuss the wait system call, and we'll see how the wait system call provides us with an interface where one process can wait for another, right? So the whole point of the two examples that I showed you, first we talked about the Unix shell, where the Unix shell waits for the current command to finish execution before proceeding on to the next command. And in this piece of code that we saw, although we wanted like the parent process to wait for the child process, obviously that is not happening, right? In the Unix shell that was happening, clearly there was some the shell is using a mechanism, waiting interface. But in this piece of code that we wrote, we wanted the child to go first, we wanted the parent to wait for the child, right? We don't know about the interface, how the wait system call is used, right? So that is why our code is not behaving the way we want it to be. We want the dots to be followed by zeros, but they are kind of jumbled. In the Unix shell, we saw that the shell is properly waiting for the command to finish. So the Unix shell is using the wait interface. So let's now, having understood why do we need the wait interface, why one process would want to wait for another, we have understood that part. let's go and understand the wait system call API and see how we can use that. So now let us see the wait system call. How does its API look like, right? So here is the function declaration for wait. So as we can see, the wait system call, what is its basic job? So the wait system call suspends execution of the calling process until one of its child terminates, right? So let's say we have a process and it has one or more children, right? When the calling process calls the wait system call, its execution will be suspended, it will be halted until one of its child terminates. When one of its child terminates, it will resume the execution, right? So what is the argument that it takes? It takes the argument that is an integer pointer, int pointer. We'll discuss this nullable thing, and then w status, right? This is the integer pointer. Basically, this is an integer pointer whose value can be either null, right? That is what this nullable qualifier says. You can pass null also, you can pass a valid integer pointer also. That is what we are saying. You have two options. You can just pass null, or you can pass a valid pointer, integer pointer. And what will this integer pointer will be used? It will be used if it is not null, right? Only when it is not null, it will store to it will be used, this integer pointer will be used to uh, s- point to the exit status information, right? So basically what it is saying is that when this is not null, when this integer pointer is not null, then it will be pointing to an integer, and that integer will store the exit status information of whom, of the child process that has just terminated, right? In the previous video we talked about the exit system call, and we saw that when the process calls exit, right, it also supplies the status, right? Exit system call takes only one integer argument, that is the exit status or the exit code, which signifies what was the reason of exiting. Was it successful or was it due to some kind of error, right? That is what the exit code is there for. And when a process calls the exit system call, it passes the exit code. So what is happening here is that uh, the wait system call takes a pointer, integer pointer, and if it is not null, this integer pointer will point to an integer, right? And that integer will be storing the exit code of the child that has just terminated. So as you can see, the wait system call will be called from the parent, and it this integer pointer will be storing the will be pointing to an integer which will have the exit code of the child that has just terminated. We'll see all of this in detail, right? So this was about the argument of the wait system call. And what is the return value? The value that is returned by the wait system call, it is again an integer. It is the process ID of the terminated child. So the whole thing is around a parent waiting on a child process. When the wait system call is invoked, the parent execution will be suspended until one of its child terminates. And when that child terminates, its exit code will be stored in this integer pointer if this is not null, and the process ID of the child that just terminated will be returned in the way in the parent process, and then onwards the parent process, after it returns from wait, can continue its execution, right? So this was a basic description of the API of the wait system call. Now let's see and understand the flow of the wait system call with some diagrams, right? So now let us understand the overall flow of the wait system call. So let's take a process, right? This is a process A, and this is the code of the process. Somewhere in the code of the process, there is a call to the fork system call. That is how it will create a child process. And we need one parent and one child to have the wait system call, right? So let's see. The process A executes the fork system call, and when it does that, we can see a new process B, which is a copy of process A has been created, right? This is what the fork system call does. It creates a copy of the original process, right? So process A is the parent of process B, and process B is the child of process A, right? Now we have two processes in the system. They are executing concurrently, right? Obviously, when the fork system call has executed, it will return in both of them, right? So now we have two processes in the system, right? Let's see what happens. What happens next, right? So next what will happen, process A, it will call the wait system call. Basically, as we saw, one process would want to wait for another process to end. So process A here would want for process B to end execution, and then only it will continue its execution, right? So here process A will be calling the wait system call. It will pass an integer pointer. Basically, it is passing the address of an integer variable, And here we will basically store, we'll use this integer variable to store the exit code of the child process when it terminates, and it will also return the process ID. So first let's see the wait system call. This is the wait system call. It is accepting an integer pointer, right? The parent process A invokes the wait system call, and then you can see wait system call suspends the execution of the calling process until one of its children terminates. So I have like changed the color of process A. It was initially blue, which means it was executing. Now it is gray to signify that process A has now halted. Its execution has now been suspended. It will now just wait, right? So now let's come back to process B. Process B, which is the child process, it will continue its execution. It will do its task. And after some time, when it has finished with its work, it will invoke the exit system call, right? And it will also pass the exit status or the exit code via this integer. So exit accepts this one parameter, that is the exit code, which signifies the reason of termination. Was it a successful one or was there some error? And if there it was any kind of error, what kind of error was it? So that is all is signified by this exit code, right? So process B invokes the exit system call. As we can see, the exit system call causes normal process termination, and status denotes the reason. The S is the status, right? And when this happens, process B will be terminated. We can see process B is now gone, right? Now what happens next? So as we discussed in the previous video also, the process control block, right, of the process is not terminated when it calls exit system call. All of its resources are like deallocated, right? When a process invokes the exit system call, all of its resources, the memory, the CPU, the IO devices, the files, all of that are deallocated except for the process control block. The process control block is kept. And why is that kept? It because the exit code of the process that has just terminated is stored in the process control block, right? We know that the process control block is a data structure. It's a where all of the information that is associated with the process is kept, right? Since exit code is a important piece of information that is associated with the process, it is kept in the process control block, right? Now let's see how this exit code will be collected by the parent, right? So what we have just discussed is that the process, although has terminated, is its process control block will still be there in the system even after its termination, and the exit system call will store this exit code in the process control block of the process that just terminated, right? So PCB of the process is not deallocated upon exit. All the other resources will be deallocated except for the PCB because it's used to store the exit status, right? So we have this PCB of the child process which got terminated, and we have the exit code. Now let's shift our attention back to the parent process. So as we discussed, if the integer pointer that is being passed by the parent process, right, this integer pointer that you see, if this is not null, which means that we are passing an address. This ampersand s is the address of the integer s. This is a valid address to an integer, and this integer pointer is pointing to an integer. Obviously, we will store the exit code in that integer that this address is pointing to. So if this status is not null, basically if this is a valid address, right, it is not a null address, then wait system call will look into the process control block of the child process that just terminated, find its exit code and store it into the integer that is being pointed to by this address, right? So this is how the wait system call has collected the exit code. Once wait collects the exit status from the PCB, it will be deallocated, right? We saw that this PCB is no longer required once the exit status had been stored in the in this point integer that is being passed, like that is being pointed to by this pointer, right? So the wait system call has collected the status and stored it in the integer variable that is being pointed to by this address, right? That is the s variable, right? Now, once that is done, we will return to the parent process. And as you can see, after wait returns, the calling process resumes execution. So till the previous slide, as you can see, process A was in gray color, and it is being signified that process A is currently halted. Its execution has been suspended. But now that the child process, one of its child process has terminated, and we have also collected the exit code, right? The wait system call has collected the exit code. Now it will return, and you can see the process A can now resume its execution, and it has the exit code of the child process. So why is this exit code useful? Because now the parent process can see what happened to its child. It created a child process, and only by examining the exit code it can know what happened. Was it successful, or the child process that it created terminated due to an error, and then it can inspect that value and take appropriate action, right? So this is how the parent can know whether the work that it was trying to do via its child process was successful or not, right? So this is the overall flow. And finally, one more thing is that the process ID of the terminated child is also returned by the wait system call, right? So there could be many children for a given process, and to know which one has terminated, the process ID of the one that just terminated is also returned to the parent process. So now you can see how the wait system call provides an interface for a process to wait on one of its children when one of its children terminates. So basically, when a process calls wait, its execution is suspended until one of its children terminates. When one of its children terminates, its exit code is, as well as the process ID of the child that just terminated, is returned to the process, the calling process, which can inspect the exit code as well as the process ID and then take appropriate action, right? So this is how the wait system call works, right? So now let's see some examples. We'll see some code examples. We'll go back to the piece of code that we were talking about and see how we can apply the wait system call there to get the desired output. So let's come back to this piece of code and see how we can have our output that we desired. Like we wanted all the dots to be printed before all the zeros, right? The child process should go first and then the parent should go. That is what we desired, but we did not have that. But with the wait system call, we can implement this. So before I show you the solution, let me also show you one piece of code that I forgot to. So here we had like the dots and zeros being printed for only 1,000 times. I wanted to show you what if we have an infinite loop, right? What if we have an infinite loop, that is the dots and the zeros will be printed forever, like as you can see, while one, right? While one, print dot or print zero. So I just wanted to show you like what is happening when both the parent and the child are executing concurrently, right? So as you can see, this is the output that is being generated. The zeros and ones are being continuously printed, and basically what does this signify is that when you have a process create a new process, right? You have a parent and a child process, then both of them are executing concurrently, and there is the way in which they will execute, the order in which they will execute is kind of non-deterministic. It is determined by the scheduler. Every time I run this piece of code, the output would be different, right? And you can see the parent and the child are going at the CPU in turns, right? And the amount of output, that amount of time that they will get to execute on the CPU is also non-deterministic. It is determined by the scheduler. So this is how the things will be without wait. The parent and the child will execute concurrently without any order as such, right? So let's see the wait system call in action and see how using the wait system call we can get the desired output. So as you can see here, the only thing that I have introduced in this piece of code is this statement wait null. Everything is the same. We have a fork system call. There is a for loop that goes for 10,000 iterations. There is a dot printing, there is a zero printing. The only statement that I have introduced in this piece of code is this wait null. So I'm not, we don't care about the return value. We are also not caring about the exit code. It's a simple wait statement. And what does a simple wait statement do? It will suspend the execution of the parent process. You can see the wait is inside the else part, right? It will suspend the execution of the parent process until one of its child process terminates, which is this one. So when I execute this piece of code, the dots would be printed before the zeros. As you can see, let me reduce the number of zeros, let it be, right? So as you can see, first all the dots were printed, 10,000 dots and then 10,000 zeros, right? So here, every time I run this program, the output is deterministic. It will always be dots followed by zeros, right? So this is how you can use the wait system call and have one process wait for the another. And in this way, you have control over the outcome of the program. In this way, things are now deterministic. Every time I run this program, I'll get the desired output, that is zeros follows by dots followed by zeros, right? So now like basically without the wait statements, it was up to the scheduler, like which process will execute in what order, how much time it will get to execute. But now with the wait statements, it is guaranteed that the child process will get to execute first. So one small clarification that I would like to make is that in this case, the parent also can get scheduled on the CPU. That is, it can go first. If the parent goes first, right? If the scheduler selects the parent to execute first, it will execute this wait and then it will get suspended, right? And so even if the parent gets to go first, it will get suspended and then the child will start execution, finish the execution, and once it finishes, then the parent will go. The other thing is that the child can go first for execution, right? So whatever is the case, before whenever the parent gets to execute on the CPU, it could be like the child has not yet finished execution, it has just printed, let's say, 5,000 dots, and it gets like the CPU gets deallocated from that process and it is assigned to the parent. The thing is that even if any kind of randomness exists, even the first statement that the parent will execute is this wait system call, and it will get suspended. So we have a guarantee that only when the child has finished its work, then only the parent will go. So the output is deterministic. Even though the order of execution might vary, the output is deterministic because the parent will get suspended the moment it gets to execute. So all the dots will come first, then will come all the zeros, right? So this is how, using the wait statement, we can remove the non-deterministic that executed in our code, that was present in our code. So let's go back to our slides, and as we can see, this is the piece of code that we had. We wanted all the dots, 10,000 dots, to be before printed before the 10,000 zeros, and with this simple piece of code that was not possible. Here there is non-determinism in the output, but if we introduce this one wait statements, we don't need to give anything. A simple wait null is sufficient. Using this wait null, we ensure that the child process will do its work before the parent. Even if the parent gets to execute on the CPU first, it will get halted, right? So this is how, using a wait statement, we can first of all have a deterministic output. We can make one process wait for another and do the job in the order that we want. So now that we have studied about the wait system call, I wanted to show you the overall flow, like with all the system calls combined, like fork, exec, exit, and wait. I wanted to show you the how the flow looks like with all the four system calls combined, right? So let's take an example. Here we have a process A, and the first system call that we'll put in this example is the fork system call. So let's say process A invokes the fork system call, and when that happens, a copy of process A will be created. So it will look something like this. So as you can see, when process A returns, it will return twice, since it's the fork system call. Here it is returning in the original process, and here it is returning in the child process. So process B is the child process of process A. Now we have two distinct processes, and both of them are identical, right? Process B is executing the same piece of code as process A. So this is how the scenario looks like. So now let's include the second system call. I'll include the wait system call into the picture. So let's say process A, which is the parent process, wants to wait on the child process, which is process B. So process A invokes the wait system call, and as you can see, the execution of process A is suspended, right? It is halted, right? Then next, what will happen? Next, process B will get chance to execute on the CPU. Let's now include the exec system call. Since process B is a child of process A and it was created via the fork system call, before calling exec, it would be executing the same piece of code, but generally we want the child process to do something which is different from the parent process. So we'll use the exec system call, and it will not create a new process. It will replace the program that is being executed by process B. So that I have shown by changing the color. So initially the light blue color indicates that the code that is being executed is the same as the one which is being executed by process A. Then process A calls wait, and process B calls exec. So the child process is now executing some other piece of code. And finally, when the child process exits, right, it will call the exit system call, and it will terminate. And when that happens, process A, which had called wait, as you can see, it will get unblocked. So whenever one of its child process terminates, the process which had called the wait system call, it will resume execution. So as you can see, this is how the overall flow looks like. And here what happened is that the parent goes first and calls wait before the child exits. So there is, in this case, the parent has called the wait system call before the child process terminates, right? So let's see the other possible scenario when the parent basically the child exits before the parent calls wait. In this case, the parent has called wait before the child exits. There is another possibility of flow where the child exits before the parent calls wait. Right? Let's see that scenario and see how the wait system call works in that case. So I'll take the same example. We'll go through the same flow. It's just that what we'll do in this case, we'll reverse the order of exit and wait. Here, the child will exit before the parent calls wait and see how uh, wait and exit behave in this case. So we have process A. Process A calls the fork system call. It creates process B. Then process B goes and executes the exec system call. So it will now execute some other piece of code. So you can see both parent and child are executing concurrently. Process A is executing some other piece of code. As you can see, we have a different color. Now, before process A calls wait, before it has a chance to wait on the process, like the child process, process B exits, right? So what happens now? So when now process A calls wait, it will return immediately, right? It has no reason to block itself because its child process has already terminated. The exit code is already available in the PCB of the child process. So when process A invokes wait, the process A does not need to get blocked. Its execution will not be suspended. The exit code will be collected from the PCB of the child process, that is process B, and process A will immediately return, right? So these are the two possibilities that exist between the wait and the exit system call, right? Either the parent process can execute wait before the child process exits. In that case, as we saw, it will get blocked, right? And only when the child process calls exit, it will resume its execution, right? And the other case is that the child process can exit before the parent process calls wait. In that case, the parent process will immediately return when it calls the wait system call, right? So this is how the wait and exit system calls behave. And we also saw all the system calls that we talked about in one picture. We saw fork, then exec, exit, and wait, right? So this was about the flow. One last thing that I want to discuss is that what does the wait system call do with the exit status? So to show you what the parent process can do, basically how the parent process can get the exit code of the child process and inspect it, I have a piece of code for you. Again, it's a simple piece of code written in C. Let's understand this. So here we have a fork system call, right? And the fork system call is basically included in an if else branch. So if the fork system call returns 0, which means we are executing in the child process. And what we are doing in the child process, we are printing a statement, that is we are inside the child process, and I'm doing a division. Doing a division by 0 that should result in an error, right? Exception basically. And in the else part, basically I have an integer, that is w status, which is basically wait status, and I have another integer process ID. So here we, as you can see, we invoke the wait system call, and the argument to the wait system call is not null. It's a pointer. It's an address of an integer variable, right? It's a pointer to an integer. So this is a non-null argument that we are passing to wait. And as we saw in the video earlier, that the wait system call will include the exit code of the child in this w status integer variable, right? And then we can inspect this integer variable to see whether it is 0. If it is 0, then it is a successful execution. If it is non-zero, then it is a there is some error, and that we can inspect. So we are printing the process ID and the wait status. So basically, the idea is that if the argument to the wait is not null, so this is the argument to the wait. Instead of passing null as we saw in the previous example, we are passing the address of a valid integer variable, that is w status. So the wait system call will put the exit code of this child process that we are creating in this w status variable, and that we can inspect. So you can see we are inspecting the variable's value. If it is 0, we can detect that it was a successful execution on behalf of the child process. If it is not, then there is some kind of error, and we are expecting an error. We are dividing by 0. So let's see how this piece of code behaves. So here I have this piece of code. Let me execute this and see what happens. So this is the command that I'm going to use. I'll clear the screen and I'll compile this piece of code, wait underscore 2, and we'll execute this wait underscore 2 binary, right? So let's see what happened. So first of all, there is a warning. The compiler is throwing a warning that we have a division by 0, right? But it will proceed. It is just throwing a warning. It's not a compilation error. So we see we are printing this message in the child process. The child process goes first, prints this message. Basically, even if the parent process goes first, it will wait, right? It will wait for the child process to finish. So the output of child process will always be before the parent process, because we have included a wait system call. This wait system call will suspend the execution of the parent till the child process terminates. So what happens when the child process returns? It is returning the process ID and the status, and we are inspecting the value of status. So what was printed? The child process, the process ID of the child is 25322. It says it exited abnormally with status 8. So this part, the else part, was executed. Obviously, the exit code is not 0. There was some kind of error. Obviously, we are expecting that we divided by 0. So there was a uh, error, and it was an abnormal termination. So this w status is non-zero. Its value is 8. Right. So you can see how the parent process can inspect the value, the exit code, and then it can take any action, right? So let me talk about a few things. You can disable this warning by including a flag which is called -w, and it will disable the warning, right? Even if you're executing the piece of code, it is not giving you warning. The second thing that I wanted to say is that let's change this. Let's do this 1 by 10. Now this is not an error, and we should get a exit code 0. That is, it should be a successful execution. So let's execute this piece of code and see whether this exit code of 8 becomes 0 or not. As you can see, it indeed becomes 0. We are now printing in the child process. Then in the parent, we are printing the PID, and it says it exited normally with status 0. Right. So if there is an error, it will terminate abnormally. If it is not, then it will say like it will be a 0 exit code with a success. I can again change it back, and it will again become the exit code of the child process will be like error, right? You can see it is non-zero 8. So this is how, if you pass a non-null, if the argument to wait is not null, the child's exit status is stored in it, and as a parent process you can inspect the exit code and determine what happened. You'll also get the process ID of the child process which terminated, right? So guys, this was it about the wait system call. We started this video and saw the like examples when one process would like to wait for another. We saw the example of the Unix shell. We also saw an example where we had to print dots and zeros, and we wanted the dots to be printed before the zeros, but that was not happening without any explicit call to wait, right? We saw that the child and the parent process were executing concurrently, and we did not have control over the output. Then we talked about the wait interface. We understood how the wait system call works, and then we included that wait system call in that dot and zero examples, and saw that now that we have control which process, like we wanted the child process to go first, and that we were able to achieve by introducing a wait system call in the parent's code, right? So there we made the output deterministic the way we wanted. And finally, we talked about the flow of the wait system, like flow of system calls. We took an example where all the 4 system calls that we have studied till now, fork, exit, and wait, we included all of those. And we saw 2 cases in which, in the first case, we had the parent call wait before the child exited, and we saw how the parent's execution gets suspended till one of its child terminates. We also saw the flow in the second case, when what happens if the child exits before the parent calls wait. In that case, the wait does not have to get blocked, it does not have to suspend the execution, it returns immediately. The final thing that we discussed in this video was that how, if you pass a status, if the argument that you pass to the wait system call, if it is not null, then you can get the exit code, and then that which you can inspect. You'll also get the process ID from the wait system call of the child that got terminated. So guys, this was it for this video. Thank you very much for watching. I'll see you in the next video. Thank you.